Okay, I think we're good to go. So welcome everybody to our first SAEON Seminar of the year. And as you might have noticed, it's being recorded, so it's going to be put up on the SAEON YouTube page. So if you want to watch it a little bit later, or if you want to see any of the other seminars, you can go have a look up on the SAEON YouTube page. And today we have Dr. Tamaryn Morris. So she's from SAEON's Egagasini node, and she's a physical oceanographer. Can't you hear me? Is there anyone else that can't hear?
I can hear.
I'm fine. I can hear you.
Okay. If you are having issues, maybe just have a look where the mic is. There's sometimes you need to say join with computer audio for you to actually be able to hear. Okay, so today's presentation is by Dr. Tamaryn Morris. So she's a physical oceanographer with a lot of in-field experience on different ocean platforms in the oceans around South Africa, and using a variety of ocean observing instruments and platforms. So she is the Ocean and Polar Coordinator at SAEON Egagasini node. And she's in a very good place to tell us all about the ocean observations that are happening in Southern Africa, and about some of these fantastic robots collecting really cool data and where we should be deploying them. So over to you, Tammy. I'm excited to hear a bit more about all these cool robots.
Thank you, Caitlin. So firstly, I'm going to just take a leaf out of Jay. The Fantastic Beasts franchise, because we're going to talk about some fantastic robots. So it's a bit sneaky of me, but also to say that this is done in collaboration, this particular presentation, with Juliet as the node manager. But you'll see as I go along, and you'll probably recognize a lot of the projects that some of you may be involved with already. There are a lot of collaborators involved with ocean observations around Southern Africa, because no one group can do this by themselves. So right off the bat, I'd like to say thank you to everybody, even though maybe not mentioned explicitly. This is truly a South African initiative. Oh, let me see here. Aha. So I'm going to take Simon Sinek's Golden Circle. I'm not sure if many of you know the book, but he wrote a book called We Start With Why. And he's a leadership guru who looks at different ways of being able to empower people to do what they need to do in their particular fields of expertise. And his book goes around this golden circle. And the first thing to do is ask why. Why are we doing what we need to be doing? So we're going to look at this from the point of view of the ocean, obviously. And so we know that the Earth is 70% water, first and foremost, and this is the first thing that you need to keep in mind. And in 1972, the Apollo 17 astronauts actually took a photo of Earth as they were traveling towards the moon, and they called it the blue marble. And from that point onwards, I think humanity finally realized that, you know, this is not Earth, this is actually this is our oceans. This is the most important part of our ecosystems, is our oceans. Okay, well, you know, those of us that are very biased towards the oceans. But then the very nice thing about this image as well is to see the interplay between the oceans and the atmosphere, the clouds, the bands. You can even see a tropical cyclone off of the Indian subcontinent. And so we learned a lot just from this one image already. Okay. The next statistic I'm going to give you is 90%. So the oceans have taken up 90%, over 90% of the heat we have generated anthropogenically over the last few decades. And this is a lot. How much? We're going to figure that out. So if we look at the annual mean, and you don't worry about all the details and the zettajoules and all the rest of that. The important thing is to note how the heat has increased as an annual mean from sort of the early 60s all the way up into where we are now. It has been a great increase. And from about the late 90s, we've crossed over and it's starting to get warmer and warmer, right? So what are we talking about here? I mean, these numbers are crazy big, and we don't really understand, you know, what we're actually dealing with in terms of heat. If we take the atomic bomb, and those of us that have watched Oppenheimer recently will appreciate the magnitude of what went into creating this large weapon. The atomic bomb gives off 1.5 10 to the 13 joules of heat, right, of energy into the system. This is a lot of heat. But if we look at what a zettajoule is, just one zettajoule is 1,345 of these atomic bombs. And if we look back at this particular graph again, and we look at those bar graph of the red lines, without having to do the maths, I'll leave you to do the maths if you really want to, but the bottom line is we are literally boiling the ocean. So this is our why, okay? We appreciate this fact now. So what impact has that warming had? You know, this great warming that we've been inputting into our oceans, what has that had on us as society? Well, we're seeing an increase in tropical storms, tropical cyclones, whether you call them typhoons, hurricanes, or tropical cyclones. It all amounts to the same thing, vicious storms that move across the ocean basins and collide into our continents. And in the Northern Hemisphere, they're by far stronger. You see the Category 5 storms concentrated around the Kurusha, Japan, China, and into the North Atlantic, crashing into Miami, into Barbados, into all of these places. But we're starting to see an increase in the intensity, frequency, and duration of storms in the Southern Hemisphere, in our Indian Ocean basin as well. And this cannot be more clearly stated as with Cyclone Freddy last year, which is one of the longest, if not the longest living tropical cyclones in our ocean basins. And it entered across Madagascar, causing a whole lot of damage, but then across twice into Mozambique, moving into Mozambique, coming back out again across the Mozambique Channel, and then up into the northern Mozambique area. This is unprecedented. It hasn't happened before. And this is purely as a result of warmer sea surface temperatures. What we're also seeing is an increase of marine heat waves. And this is a map that Mercator Ocean and Copernicus Marine Services put out quite regularly now, is to look and track marine heat wave events across the ocean basins. It's a very coarse resolution, so if you had to zoom in, it's going to be difficult to see. It gets very pixelated. But the bottom line is this: it's starting to increase heat in the tropical regions, yes, but you're starting to see them in the subtropical temperate regions as well. And this has a direct impact on our fisheries, our biodiversity, all sorts of living creatures, living things within our oceans, all right? We're also seeing sea level rise. So if you warm the ocean, you expand the ocean. And when you expand the ocean, it rises. We won't go into all the detailed science and maths around that. So we're seeing a sea level rise. It has a knock-on effect because a warmer ocean also destabilizes to some degree and will eventually help melt the ice in both the Arctic and the Antarctic. And we've seen those news reports and articles coming through on all sorts of news channels, how, you know, we're starting to see more ice or more water coming off of the ice shelves. So it has a double whammy effect, if you were, this warming of the ocean. We're seeing an expansion causing sea level rise. We're also seeing melting causing more sea level rise. And we've had a 10-centimeter rise in the last 30 years, okay? It's not uniform across the oceans. You'll see in the map, those areas that are in red have experienced a higher sea level rise. Those in blue are lower. So it's not a uniform effect. It's now rising by 10 centimeters everywhere, but it is causing a problem. And we're going to see more and more communities being drenched and flooded. Remember, nearly 40% of our global population lives close to the coastline. So where you've got tropical storms, tropical cyclones, storm surges, extreme waves impacting these coastlines, with the sea level rise, it's going to be able to push along forward, okay? And now keep in mind very clearly, I've only spoken about temperature here. I haven't touched the changes in nutrients, biogeochemistry, carbon, the work. So remember, we've got a lot to deal with in terms of the oceans. So I think I've convinced you of the why. We now need to look at the how, okay? The next part is we have a big problem. There's no doubt about this, and I don't think anybody on this particular call would doubt me on that one. But now we need to look at the how. How do we go about sort of tackling and understanding this problem and, you know, at least mitigating against the worst of these issues? So the first thing to note is the Global Ocean Observing System was set up a number of years ago now. It's funded by the International Oceanographic Commission. It's a governmental oceanographic commission, my apologies, and the WMO, the World Meteorological Organization, as well as other science organizations. And they look after, or they help put out into the oceans at least 13 ocean observing systems, right? And they're listed over here. And these are collecting information from the global oceans, from ships of opportunity, be they container vessels, fishing vessels, things like that, autonomous instruments, the really cool robots I'm going to talk about in a little bit, moorings, buoys, floating buoys, repeat transects, things like that, research vessels that are doing very high resolution, detailed studies of our oceans. And so all of this data goes back into the Global Ocean Observing System. It is all freely available. Remember, this data has to be made freely available to be a part of GOOSE. And this data feeds directly into national or global meteorological models. So the pressure from the sea surface pressure from this particular data sets, or these data sets, are used directly into our weather forecasting, climate forecasting systems on a daily basis, right? And so you look at this and you think, well, great. I mean, look, there's a wonderful lot of observations going on in the North Atlantic. There's loads in the North Atlantic, even to some degree in the North Pacific Ocean. But if you look closely at the Southern Hemisphere, there's a large portion of white. So the Southern Hemisphere is understudied, it's under-resourced. We do not have enough observations. It impacts our weather and climate forecast, and it impacts what's happening. Those of us that live in Cape Town, we know this to be a fact. We have systems that come in, and as best as we can try and figure out what's happening. But, you know, we need to be understanding our oceans a lot better in order to prepare our societies for what's happening, okay? So I'm just going to focus on 3 of these 13, and you're welcome to go and have a look or ask questions further about others. But these are the really cool ones I wanted to talk about, and things that we can start doing within our own, within South Africa, or what we're going to be doing going forwards. So the first of these just happens to be my favorite, and that is the Argo float. It's a robot that stands about as high, just a little bit shorter than me, so quite short if you're a tall person. And it's a free-floating autonomous robot. So they get deployed from vessels. They could be research vessels, but you can deploy them fairly easily. They weigh about 25, 30 kilos, from fishing vessels, container vessels, all sorts of things. So we try and get them out in as many places as possible, right? And they drop down, they descend to the drifting depth of about 1,000 meters, and they stay there for about 9.5 days, okay? And they just bob along. They're collecting data while they're down there. And then at a certain time, they drop down to 2,000 meters, and then they do an ascent to the surface. And here they're collecting data. They're collecting a profile of temperature and salinity and pressure. And on the bigger floats, you will get additional sensors such as nitrate, pH, chlorophyll A, and things like that. These are the BGC Argo floats. So there's less of those in the ocean. There's more of the core Argo, which is temperature and salinity, right? And these are the ones we need to understand water masses, sea level rise, etc. So they free float. They come up to the surface, they drop off their data, and once they've done that, they drop back down again. And they can last in our oceans for 4.5, 5 years. Some of them have lasted as long as 7, 8 years. So we manufacture, or the manufacturers now make them with lithium batteries to ensure that they last as long as possible. And they're fantastic. The trick here is they're free floating, okay? And they are not retrieved again. They float along until they eventually, their battery runs out, and they sink to the seafloor. And before you ask me the questions about ecological waste, there has been papers written about this, but we can discuss it later. So these are incredible. How incredible? This is a screenshot of 100 years of data collected from vessels, primarily research vessels, yes, but where they've done a profile to at least 1,000 meters. Okay, so now remember, my Argo floats are going from 2,000 meters up, and the deep Argo can go from 6,000 meters to the surface. So this is just a map looking at 1,000 meters. This is taken from the World Ocean Database, and you can see here just over 500,000 profiles globally in 100 years. And you can see an intensification of study around the Kuroshio Current off of Japan, the Gulf Stream off of America, far less in the Southern Hemisphere again. If we look at Argo floats, and Argo was first deployed in 2000, by 2015, we had over 1.5 million profiles, and by 2018, we had over 2 million profiles. And you can see the density, the amount of information that's come back. And purely from this data set, they've been able to work with the IPCC and to actually get a state of the ocean reports out to understand exactly how much is happening. Those sea level maps, that sea level rise maps that you saw earlier, is based almost primarily on this data because we've been able to collect this information. But we need to continue collecting it because we need to understand what is changing, how fast it's changing, things like that. So you can see how valuable the Argo float, the Argo database is. At present, at any given time, there should be over 4,000 floats within the ocean, and they're looking to increase observations in very difficult areas, such as the equator, where you've got floats that will diverge away from the equator quite quickly, western boundary currents, such as the Egagasini, things that move very quickly. So we want to understand as much as we can, okay? And in South Africa, we've only bought 2 Argo floats thus far. SAEON bought 2 in 2009, and we're looking to try and buy more now through the programs coming up, which we'll talk about later. But we have been deploying floats on behalf of other countries. So those countries that are able to purchase floats, such as the French and the US, European, the Germans, they send us their floats, and you can see here a lovely picture of the bosun on the SA 2 deploying one of the floats. This particular boxed float disintegrates in the water, and the float free floats away. It's a way of being able to protect them a bit better. But we've done a lot of deployments on behalf of others, and we've been able to increase the observations, particularly in the South Atlantic, into the Southern Ocean around our area. Okay, so that's Argo floats. The next one is a buoyancy glider, which works in a very similar way to an Argo float, except that this one is controlled by a pilot, a glider pilot. So it will free float to a certain degree in strong currents. We do struggle to pilot them against pretty strong currents or within eddies, but the glider pilot is able to then direct the glider to go to a certain waypoint. They're able to do transects across coastlines, in and out of embayments. They're able to do transects across various process sites, such as plankton blooms in the Southern Ocean and things like that. And so they're fantastic at trying to get really detailed observations. A dive, because they dive to about 1,000 meters, a full dive takes about 6 hours up and down. So that glider piloting is a 24-hour job. Gliders are more expensive than Argo floats, but purely because we can retrieve them again, service them, redeploy them. And so their lifetime, if well looked after and we don't lose them, is pretty good. So gliders as well have become quite useful. We also don't need to put big, expensive ships to sea all the time to be able to collect information in high resolution. And we can, the modular systems that some of these gliders come with, you're able to couple additional sensors onto it. So this is new technology that we're also hoping to get soon within the SAPRI fold. South Africa has purchased a few of these in the past through the SACO program. And these have been deployed in various missions up until now. We did, Marjolaine did 2 studies on the east coast of South Africa, one called Gina and one called Sage, which actually put these gliders into the Egagasini current. And this is where, when I tell you that they struggled to pilot, the aim of the exercise was to try and do zigzag patterns across that shelf, and you can see it does get a bit chaotic at time. And she also did a study that left Richards Bay area down towards the Egalis. So some of you may have been part of that retrieval team off of Argo Bay. And then they've also done a fair number of studies into the Southern Ocean across the fronts to look at seasonal blooms and things like that, to try and understand what is happening in our Southern Ocean in terms of biogeochemistry and iron. So I would encourage you, if you want to know more of these particular experiments, is to go to the SAEON website and have a look. So their fleet is diminished somewhat now. They do, obviously, over time, they do need to be serviced a bit more and things like that. So we're hoping to get some more gliders and to continue this work and other work, which I'll talk about in a bit, some more. And then last, but certainly not least, and this is maybe not a robot, but we stick a whole lot of instruments onto a particular line, is that of subsurface moorings. And we have a brilliant picture taken by one of our students on a cruise where you can actually see the top float crashing into the water as it's being deployed. So these floats, these moorings, we can do them in various ways depending on what we're looking at. But the idea is to be able to take a long cable, short cable, depending on where we're deploying, with reference to the Al-Wandle team. And we've got buoyancy, but we can put current meters, we can put temperature sensors, we can put microcats on it that collect salinity as well. We can collect a whole lot of data from these particular instruments. The downside with some of the subsurface moorings is obviously we only get the data back once we retrieve the moorings back to the surface and download all the instruments. There is method of being able to do near real-time buoys moorings, but this obviously gets quite expensive and is very valuable, but for very deep moorings gets difficult. So this is another really key way of being able to get information in very hard to reach places. But because it's a difficult exercise, you need a ship, you need all the instruments, and can be quite an expensive exercise. The idea is to put moorings in very key places where it gives the most information as what is needed. But we, as a group, as a team, quite a few of us have been involved with various mooring exercises. The bottom right shows a mooring array that was deployed in the Mozambique Channel by the Dutch team many years ago, but we were part of that. We learned from them. So we have that knowledge, we have that, we're gaining that technology now, and we're able to do quite a few of these sort of exercises. Okay. And in South Africa, we had the ASCA array a number of years ago, from 2015 to 2018. And this was a series of moorings, some of these deep, long, tall moorings, what we call tall moorings, but also some shelf moorings, so a bit shallower, and some sea pies work, which is like a mooring. It just sits at the bottom, giving pressure. And so that exercise is in the water for 3-4 years, and it's an expensive exercise to put back in, and we're looking to try and at least put some of the key sites back in the next few years. The Samba mooring array, which is run by DFFE and UCT, that's been in the water now for nearly 10 years. They've had moorings out into the South Atlantic Ocean. And so that's a fantastic data set already that's looking at that leakage of the Egalis current as it moves into the South Atlantic, providing heat to the Northern Hemisphere. There were a series of moorings out on the Good Hope line, and this is the line that goes down towards south to Antarctica. And this was primarily run with UCT, DFFE, but as with collaboration from some colleagues in France. And then the Crossroads line didn't have moorings on it, but it's a line that gets completed with CTDs and XPTs every year when the vessel returns from Marion Island. And it's important little data set by now, because it's not often that you can get data that goes across the Egalis current, which is going down along the coast and then retroflects and makes the Egalis return current. That's the one that goes in sort of a zigzag across. And to get both in one snapshot is not always easy. So these data provide a wonderful look at what the currents are doing around South Africa. But I don't want to leave out, I mean, a lot of these instruments are incredibly expensive, and it's taken us a long time to build the business plans and to build the business cases to have them. But what's happening around the world, and we've got leaders within SAEON that are driving this, is the use of low-cost technology, not low quality, low cost. So being able to put temperature sensors onto fishing nets, being able to put weather sensors onto additional vessels that could be collecting that data and putting it out into the ocean. There's a number of really cool ideas that are coming through now, the open CTD system, the Fish Oasis, that are able to collect data for what we're needing, particularly, especially in the coastal zone, but also out into the offshore, and making that available back to society, because the fishermen really would love to know what's happening in their ocean. So if we could start working with them, it's a win-win situation, but also back into that global ocean observing system. Can we augment that data up to be able to look at our weather, climates, and all sorts of other information as well? And so just a nod quickly to Jethan and the team who are working on a collab project, which is basically a lab in a box. Coastal laboratory in a box. And so this is an idea of being able to collect data fairly at a low cost in more coastal areas around, particularly Africa, but around the world. Okay, so the final part of the golden circle is what? But I want to change that and say where. So we know why there's a problem. We know how we're going to fix this problem, but where do we put the instruments in order to be able to help us look at what we're dealing with? So the first of these is SAPRI, and SAPRI is the South African Polar Research Infrastructure. This was recently initiated. Took a long time to write the proposal, the business plans, and we've got this going since 2021 now. And we're making use of already established lines. So those lines that are going out to Gough Island, down to Antarctica and Tamaryn Island to deploy instruments. So we've been deploying Argo floats along these lines. The SACO teams have been deploying gliders along the Sinai lines. And so we have been collecting data. And what we want to do is make sure that we keep collecting data. What else can we be contributing in terms of robots, in terms of observations in the ocean that would could come naturally without taking away from that ship's time, without taking away from too much of the scientist, the detailed science that needs to happen. So we want to be able to collect data on the side, if you know what I mean. So really good observations of the ocean atmosphere, and we're working with teams from SAWS and within SAEON to have additional instrumentation on our vessel. We also want to be doing additional work along the ASCA line, which is that little yellow one that we're hoping to reinitiate soon. Then working with the SMACRI team, we've had some lovely discussions over the last little while, working in the Sentinel sites within Algoa Bay, Natal Bight, and within the Western Cape, and looking at putting additional sensors onto their small boats so that we're collecting information, working with them in terms of the oceanography, you know, how can we support things, but also being able to deploy drifters, those instruments that don't need depth to be collecting data. So you'll appreciate Argo floats and gliders might need a bit more depth to get some really good information out. But you get surface gliders, you get surface drifters, and all of that information could tell us a lot more about the circulation in these near coastal regions and things that are difficult to understand. We're also looking to develop low-cost sensors that we can work within our coastal communities and create citizen science projects in terms of the physics, the oceanography. So another thing that we're involved with is within Goose, they've got 3 UN Ocean Decade projects. So one of these is the co-design project, and I co-lead the boundary currents exemplars. So there's 6 exemplars: boundary currents, marine heat waves, tropical storms, marine life, carbon, and the other one, can't think off the top of my head, is storm surge, which also impacts South Africa quite a bit. So with the co-lead of boundary currents, we chose the Greater Agulhas Current region as our pilot, so that, and the aim is to get sustained ocean observing technology into the Agulhas Current. And by sustained, I mean not in a 3-year research project manner, but trying to keep those instrumentation in key regions for as long as we can, you know, forever if we could. So what we need to do in order to co-design this is to work with the modeling community. Where is it best needed? Where do we need to understand information in order to complement the models? Where do we need information to complement other stakeholders, such as operational forecasting facilities, shipping and fishing communities, things like that? So it's a co-design process that has already started, but also working with other exemplars. We're seeing an increase of marine heat waves potentially in the retroflexion region. We're seeing that increase in the Mozambique Channel, where some of the water that's contributing to the Egalis current comes from. We're also seeing tropical storms, as I pointed out earlier, intensifying in the Mozambique Channel. So what observations are needed in order to complement what we're trying to do with the boundary currents, try and understand the Egalis current a bit better, but also to try and understand the other exemplars. And of course, you'll appreciate that all the heat that comes out of the Egalis current is pushing into the South Atlantic. So if we understand what's coming out, we're going to have a better appreciation for what's going into the South Atlantic and what's going back into the Indian Ocean. So this is an ongoing project. We have a number of workshops set up for this year. We've been doing a lot of work. We need to write some review papers to understand where we've been, what's been collected in the Egalis current before, what's worked, what's hasn't, where's the challenges. You saw some of the challenges there, trying to drive a buoyancy glider in a straight line across the Egalis current. You know, how do we work with those challenges to go forwards so that we can get the information we need? And then finally, we have an ASEP project that's been accepted now, which we'll hopefully start the surveys of in at the end of April. So working with our Wandle and Smackry teams in Algoa Bay, we're going to be doing a transect of stations from a small boat that's run by ASEP and SAEB, the Observer. Sure, that nearly escaped me there. And so we're going to be doing transects of CTDs and collecting zooplankton samples, collecting information. We want to be collecting eDNA. We want to be collecting as much as we can. So hands up if anybody wants to work with us. We have a really nice team building already. But at the same time, we want to understand the upwelling at the shelf edge. So one of the problems that boundary currents are facing now, and the Egalis current being one of the biggest western boundary currents, is you get what's called a sneaky upwelling. Or we call it sneaky upwelling. So on the Benguela current, we understand well the wind and the upwelling that happens when the wind pushes up. But we're seeing this upwelling that happens underneath the western boundary currents. And so you're getting these very cold shelf areas. And we want to understand what are the dynamics pushing that. We have an idea, but we will want to look at it. But at the same time, this upwelling is is pushing biodiversity onto the shelf. And so we're seeing an influx of, say, copepods and things like that are coming. We also have a Egalis current. We have the anomalies that come down, the Natal pulses, the cyclonic eddies. So I drew one on here. It doesn't look like that, but you'll appreciate when we do have a cyclonic eddy, that whole Egalis current moves offshore. And this brings a whole different dynamic to the shelf region in terms of the diversity and everything. And so we want to survey when there's the Egalis current, but also when these anomalies are coming down so we can see the difference between the two. We also want to start connecting the coastal to the offshore dynamics and environments. So our Wandle and Smackry have done an incredible job of understanding what's happening in the Algoa Bay. And we want to start complementing that and understanding how the Egalis current is actually influencing that. But it also is going to help with Somasana and Jenny's team looking at some of the modeling that's happening to be able to see what this current, this dear western boundary current is doing and how it's influencing Algoa Bay. And of course, we want to deploy some amazing ocean robots to monitor our ocean. So we're going to use this line whenever we can to be deploying drifters. We want to work with some schools to actually build some homemade drifting buoys. We want to deploy some Argo floats and if possible, even a glider that we'll have to go and collect again and see some of the dynamics that's happening across here. And so we're going to use this as a proof of concept almost for our boundary current work for co-design to see, like, if we sustain this particular line, what information are we going to have going forwards? What do we need? Is this a key site or not? Would it help to have a reference station buoy off of Algoa Bay? And these are the questions we need to start asking ourselves, answering, so that we can start looking at our oceans a bit better. And with that, I'm going to say thank you.
Thank you so much, Tammy. I definitely learned a lot about all the amazing robots in our ocean. I want to now open it up to any questions anyone has questions or just wants to chat about these lovely robots. I think the easiest way is if you do have a question, just raise your hand, and we'll go like that. Or you could also use the chat.
I'm going to leave the presentation up for now in case anybody has a particular question on a slide and I can go back to it. Otherwise, I'm happy to stop sharing and see more people if that helps as well.
People don't want to chat to us today, Tammy.
I don't know what that's about. I'm also happy to take questions by email. So if you're feeling a bit shy, a lot of the people on the call are actually part of some of these projects as we're going. And so there's a lot of inputs already, which is great. I think Kathleen
there's
got a question.
Yeah.
Yes. Hi, everyone. Thanks, Tamaryn, for this presentation. I always love seeing what's happening in the ocean, being a terrestrial scientist. I suppose my question is really nuts and bolts. This must be an enormous amount of data.
Yes.
How do you conceptualize the processing? Do you do, per instrument? Do you have it streamlined through a chain of people? You try and like group it by variable across devices or sensors, or maybe that's I was just wondering, how do you manage just from the data side of things?
Yeah, so one of the beauty of working within the Goose ocean observing system is that all of these data have to be made freely available, and because of that caveat, as you were, the Argo program is one of those that has an incredible data management system. You do have to work through data centers, and we are not one here in South Africa, so we would work through either the one in India or in France, but they have methods of being able to offload that data within 12 hours and make it available on a system. And I'm happy, we were actually talking about it before we started. I said to Caitlin, we should actually do a quick learning thing on how to access Argo float data because it's freely available for everybody. And then you get the delayed time data, which has had a year to where people have actually had a look at it to do QC control on it. So that is one method where we ourselves don't need to maybe process the Argo data. It gets done by data centers, but this is certainly not the case for all of the floats. And so it's going to become quite a thing when we start looking at data management systems. Luckily with SAPRI, we've got a data management team, but we are going to need to look at them instrument by instrument. How do we process the data, working to best practices? We've done a lot of input into the ocean best practices system, so that we have little cookbooks or methods that we can follow, and to make sure that we're doing it to those levels. So it is going to be something when we start getting all this data in, I'm going to need a whole team of experts on this. So for now, it's going to get very interesting still.
Thanks. It looks like lots of novelty in different aspects coming up.
Yeah, definitely.
Yeah, thanks so much for your question, Kathleen. I see there's a Dr. Marcus Haldenmes. Do you want to unmute and ask your question?
Hi, Tamaryn. Thanks for the very interesting presentation. So, yeah, I guess less of the oceanography side and again, more nuts and bolts question. So I was wondering, so to get the data to you, so you, on the one slide you had Iridium satellite communication listed there. So, and I know commercial, if I have to buy, get some sort of a connection for myself via Iridium just for GPS, it's already around 3,000 Rand a year, and that's for one instrument. So, and I assume you guys deal with hundreds and hundreds of instruments. So how does that work? Do you have your own dedicated Iridium satellite, or do you also just go through the commercial option, or you have, how does it work?
Yeah, so when we start with this, so on my APP, I don't know if there's anybody from admin on the call, is we have to set up an Iridium contract to be able to talk to these instruments. So hopefully in the new year, we'll have 6 Argo floats and 2 buoyancy gliders. And so we'd have to set up Iridium contracts for those 8 instruments and then some. So whatever we start adding that needs that connectivity. But you're right, it's very expensive. Funny you should mention your own satellite. When we developed the SAPRI proposal and we started on that work in 2019, CPT actually came forward and said, look, they build nanotechnology or nano satellites, and they wanted to be a part of SAPRI to create a satellite that sits over Marion Island, as an example, and allows for the machine-to-machine transfer of data from Marion Island back to, say, Cape Town. Unfortunately, as the program progressed, the lead professor at CPUT left, and so there's a bit of a gap there, but it's still something that would be really, really interesting, where we've got key regions that we want to look at. So if there's a glider close to Marion Island, it could do that machine-to-machine transfer of data as well. So it would be amazing if we could actually get that right. And it was definitely part of the SAPRI thinking at one stage, but for now, what we'll have to do is go the commercial route of Iridium transmissions, yes.
Perfect, thank you very much.
Yeah, thanks for your question. So hopefully we can get all of these robots we're putting in the ocean to chat, and we can get some data out of it. Mary Jane, I see your hands up.
Thanks, Kathleen. Thanks, Tammy, for a very interesting presentation. Can you hear me okay?
Thank you. Yes, yes.
Okay. Yeah, I'd like you to expand a bit on the, with citizen science, on the, low cost sensors versus quality, and how that translates into, say if you wanted to send your data to the ECMWF instead of the data that's used by NWP models, and how that's going, and how the low cost sensors compare to the more expensive ones.
So at this stage, it's all in development. We've been working, myself, Jethan from Alwandle, Errol, who's part of our team. We've been working to understand how to get data up through the GTS, and we've been working with Peter Rue from SAWS, who's a guru on this. So the idea, we want to start very simply and create a temperature sensor. So first things first, and actually make this temperature sensor modular. So whether it goes onto a swimmer's arm, or if it goes onto a surfboard, or if it goes onto a small yacht, for instance, that just does sort of weekend jaunts around Algoa Bay or Table Bay or whatever. And we want to try and see if we can get the sensor to work, and then how we put that data up onto where it's made available through the GTS. We'd have to work through the Goose and those sorts of networks to see if it's a possibility. We also don't want to overwhelm them with data that maybe they don't want to use. So it would be a development process. But with our connections within Goose, and particularly the Ships of Opportunity program, the Ships Observation Team, there's different ways of being able to connect that data up. But we want to start very simply at first, just with a temperature sensor, and then go from there.
Okay, great. Thanks.
Yeah, that sounds quite exciting. And coming from more the science engagement side of things, the citizen science and stuff, sounds very, very cool and promising.
Yeah, we had a great idea to be able to put together an app, and you literally, like, people who are in the water, go and collect some data on a weekend. And we do not have enough of that data at all.
That'll be cool. Cool. Does anybody else have any more questions? We're all happy. We've got a nice understanding of all the robots in the ocean.
Yeah,
Cool.
and we'll publish lots of articles so you can see our progress.
So I just want to say thank you so much, Tammy, for doing the seminar for us today. I definitely learned a lot. And thank you to everybody for joining. And please join us next month on the 7th of March for our next seminar. And yeah, thank you, everybody.
Thank you, Caitlin. Thank you.
Thank you, everyone. Bye-bye.